Cool, thank you. So usually I actually hate when people start talks by thanking the organizers, because at least for me, sometimes I take it as I'm in the audience and I'm a bit like, oh, look at you suckers that had to submit an abstract to get a talk here. But I guess everyone here was invited, so that doesn't count today. So thank you very much to the organizers for this invite. I'm very excited to be here. So I'm going to talk about, so I'm a member of the Planck collaboration, which is behind this Planck satellite, which is this cosmic microwave background probe. And most of my talk will just kind of be a very general, aimed at non-experts about Planck and about the cosmic microwave background, and some of the work that I've been involved in doing this. And so hopefully you find this useful. And so jumping right into it. So I'll start with this video, and which we'll play in a second, and which this is a snapshot of the early universe. And here we have in red are protons, and in green electrons, and photons are just bouncing around in between the different charged particles that they interact with. And this is this baryon photon plasma that was the early universe. Now, at some point, the universe cools enough that neutral hydrogen forms. There's no more charged particles, and these photons are just free to stream out into the universe, past the formation of the first stars, past the formation of the first galaxies. As the photons travel, the expansion of the universe stretches out their wavelength, so they get redder and redder. And they can be gravitationally deflected by a cluster of galaxies, like you just saw there. At some later time, actually, the universe gets reionized and there's new electrons, and some of those photons scatter off of those new electrons again. And they kind of go on in this fashion, traveling through the universe until maybe they reach the spiral arm of some dusty galaxy, and they get gobbled up by Planck. And so with Planck, we make maps of the temperature of these photons coming at us from all different directions, and we make these full maps of the sky. And this is the cosmic microwave background. So what is Planck? So Planck is actually the third one of these third generation of these satellites, following COBE and WMAP. To measure this background. And basically the important thing is that each one has just had better and better angular resolution and lower noise, and we're able to just resolve smaller and smaller scale structures. Here's a picture of Planck in 2009. And so you've got photons come in here, they bounce off of that mirror, there's another mirror there, then they go into the focal plane, which is right there. And on the focal plane, there's two instruments, creatively named the low frequency instrument, one which is observing at these frequencies here. And then in that hole that you saw here, in fact, is the high frequency instrument, which observes between 100 and 853 gigahertz. And here's to get a sense of scale a bit, with people wrapped up, ready to go for launch. And Planck was launched in May 2009. It was actually on board another satellite as well. On board this shuttle that launched was also Herschel. And at some point after the launch, actually, someone was able to actually image. So this is with some optical telescope in the Canary Islands, I believe. And you see 3 dots moving by, and that is actually Planck, Herschel, and part of the rocket that was the delivery vehicle. So they were able to see it go by. And so Planck made its way to the L2 Lagrange point, where it observed. So that means that it co-rotated with the Earth around the Sun, and but just a bit further out in orbit. And then basically just scanned in great circles, which precessed because of the orbit of around the Sun. And so every 6 months, basically, Planck made a full map of the sky. In fact, if you're curious what happened to Planck now, so Planck's mission is done. We're still analyzing data, and the collaboration still exists, but the satellite itself is done. It ran out of coolant as planned. And what they actually did was they just kicked it out a bit further, I guess to make room. I got this, I didn't realize there wasn't that much room at L2, but I don't know, they kicked it out a bit further to just get it out of there. And so now it's a bit further out, which means that it's actually lagging in orbit around the Sun. And actually the Earth is going to lap it in something like 200 years, I believe. There you go. We made these maps with Planck. of the sky. So here is a projection of the full sky onto these onto the 2D image that you see here at the different frequencies that Planck observes at. And a lot of what you see here is foregrounds. At the foreground minimum here at 70 gigahertz, you can really see these are just the cosmic microwave background fluctuations. Down here, there's radio emission synchrotron. Down here, this is all galactic dust that's just getting brighter and brighter at a higher frequency. And well, one of the really neat things of having these two different instruments on board was these were two totally different detector technologies, and really two totally different teams of people essentially. And so you can take these maps that were made and difference them and double check that you've got all your systematics right and everything. And when you do this difference, so this was from LFI, this is from HFI, and here's the difference. And in the units that we usually work in, the CMB is constant across frequencies, and indeed it cancels basically perfectly. All you see out here is noise. And so that's a really great cross-check that basically these results are right. And also you see that the galaxy and stuff like these foregrounds that are here don't cancel. So that gives you an idea of how one goes about doing foreground cleaning. You can get at some of these foregrounds with differences and then subtract them from other maps and so on. And so you do that, and you can produce these cleaned full sky maps. Here's the one from WMAP, in fact. This is the satellite that came before Planck. And here's Planck. And looking at this, you would probably say, boy, that was a waste of $1 billion. But in fact, if you zoom in, you note the difference. And so let me zoom in on a patch of sky here, which is, I believe, about 100 square degrees. Yeah, I think that's right. And not only zoom in, actually, I'm going to decompose it into different band limits. And so I'm going to decompose this map into the largest scale modes here, the medium scale modes, and the small scale modes. And these, in fact, correspond to different regions of the CMB power spectrum, which is this thing that you see plotted here, often labeled CL with some factors of L, which is the multipole moment, which is like the angular frequency. So these are small scales here and large scales here. And actually, when I plotted on this particular combination of log linear and the different factors, the area under the curve here is the total fluctuation power in these maps. And so that makes sense. This one looks like it's the intermediate scales are the most, have the most fluctuations, and indeed the area under the curve here is the most. And so now if I do this comparison, Planck WMAP, so here's Planck and WMAP, the same patch of sky. These are just the large scale modes. They look really pretty much the same, really as do the intermediate scale modes. It's only when you get to the small scale modes that you really start to see the difference. And this was all on the same color scale, but if I blow this up by a factor of 10, this last column, you can see this is all just noise. Whereas here, Planck is really able to resolve these small scale CMB fluctuations. And so you could do this not just in these three big broad band limits, but you can do this in any set of bins, and with that you produce the CMB power spectrum. As a function of L, again, small scales here, large scales here. So in blue is the power spectrum from WMAP. And as you can see, once you get to medium, intermediate, small scale modes, these error bars just blow up because of the WMAP is insensitive to these very small scales. But Planck continues in black here. The error bars are quite small all throughout here. Although even Planck eventually, the error bars do blow up. So Planck obviously doesn't have infinite resolution. And there's other experiments, for example, the Atacama Cosmology Telescope or the South Pole Telescope that are on the ground. They have much bigger dishes, and so they have even better angular resolution. So at around here, these experiments, in fact, win out. Although, as it turns out, a lot of the cosmological information is really in this range where Planck really nails this down. Right, so there's one more line on this plot, and that's this gray line that you see behind here. And that's the best fit lambda CDM model. So this is the best fit model to this Planck data. And I'm going to spend the next part of the talk talking about this model, because probably one of the main conclusions from Planck is really that this model fits this data extremely well, which is quite remarkable because these error bars are extremely tiny. And this model is but there's a lot of structure in this data. You have to get all these peaks, right? And this model is extremely simple. And so it's really remarkable that this works as well as it does. And it's based on just 6 parameters that I'll go into a bit now. So I've grouped them here like so. So there's 2 of these 6 parameters have to do with the amplitude and the spectral index of the power law of primordial perturbations set up by inflation. So there's an amplitude AS and then whether there's a tilt NS. You have 3 parameters that tell you about what's the content of the universe. There's the energy densities rho of baryons, cold dark matter, and the energy density in the cosmological constant in dark energy. And finally, there's when reionization happens, so this redshift Z re ion. Now, often, instead of these, we can reparameterize them into other more useful in various ways parameters, as long as we keep a set of 6. And so, for example, one thing that's often taken is instead of this amplitude, this primordial amplitude, this is more related to the amplitude today, AS e to the minus 2 tau, where tau is now not the redshift that reionization happens, but rather the optical depth to reionization. And this tells you the amplitude today because basically an e to the minus tau of the CMB photons were rescattered by reionization, and so square that to get the power spectrum, you get an e to the minus 2 tau. Here we often take the baryon and the total matter density, which is cold dark matter plus baryons. And instead of the rows, which have units, we work in these unitless quantities, which are just the rows with some particular choice of units. And usually you don't talk about the energy density in lambda. Rather, you take some other parameter like the angular size of the sound horizon, which I'll get into in a moment. Or often, if you have these energy densities, then you can write down the Friedmann equation and you can calculate the expansion rate. So often, actually, the 6th parameter can be the Hubble constant today. And basically, by definition, in lambda CDM, there's other parameters and things that go into this model, but these have default values, natural values. For example, curvature, which is 0, 3 neutrinos, which have a mass of their minimum given terrestrial experiments. And in lambda CDM, by default, these are at these values. And so that's what's so remarkable that this fits, is that these are at these default values. If we find, for example, that lambda CDM does not fit our data, then that's extremely exciting, because that means that there's some new physics, because one of these has to be different to fix that. So another thing that's, one thing that's really remarkable about the CMB that makes it so good at constraining this lambda CDM model is the following thing, is that basically it comes from a time when the universe was really uniform. So the fluctuations in that primordial plasma were something like 10 to the minus 5 or something like this. And that means that we get to use linear perturbation theory, which is really, really crucial. So one thing you really don't ever hear CMB people argue about is how to compute model predictions. That's definitely not true of all fields, right? We'll argue about what to put in the model, but actually doing it is like a totally solved problem. And really that has to do with this fact that we get to use linear perturbation theory. So what does that mean? Well, if you write down the equations that govern that plasma, and I've given a slightly cartoon version, but actually it's not, I've dropped one term and I've grouped a bunch of things in here, but this is actually really basically it. And so this is the equation. This big theta is just a temperature over density in that primordial plasma as a function of position and time. And so this is the equation that we use to model at very early times the evolution of this big theta. So you'll probably recognize it as this is the equation of just propagating sound waves in some medium. And there's some driving force here, which is in fact turns out to be gravity. But this is only so simple because we're working in the linear regime. So this comes from Einstein's gravitational equations and the Boltzmann equations, which are in general totally nonlinear and totally complicated, and there's been a massive amount of simplification to get you down to this. But the really nice thing here is that there's only linear orders of these thetas. And what that means is that if you take the Fourier transform of this equation, everything breaks up really neatly by different modes. So basically, I can just solve this equation now for each individual Fourier mode k, and they all just evolve independently. I solve them all independently, and then at the end I add the result. And if this was nonlinear, that wouldn't have happened. And so you'll note that this equation here is even simpler. In fact, this is now just a harmonic oscillator equation that everyone's really familiar with. It's got an angular frequency that's k times the speed. This is the speed of these waves propagate, speed of sound. And so the different k modes all oscillate at a different angular frequency. And then the final ingredient is really, what is this speed of sound? Well, if you think back to that picture of that primordial plasma, so the speed of sound there turns out to be the speed of light divided by √3. And the reason it's not the speed of light is because this isn't the speed of one of those photons traveling in that plasma. This is the speed at which the photons can move along an overdensity in this baryon plasma. And this 3 here comes from, that's the number of spatial dimensions. Similarly, at some later point when this plasma, after recombination, when the photons no longer interact with this plasma, they cease to be able to move these overdensities along, and so the sound speed just goes to 0, right? And basically, what we get is the sound speed goes to 0, these waves freeze in, and then this photon that just last scattered carries to us this information about at what point this wave is frozen in. And so, it's something like this, we see this picture of this wave frozen in time that these photons are bringing to us. So now let me take a look at evolving one of these modes. So I've picked here 3 different Fourier modes. And so now I'm thinking this is not a map of the sky. This is now a slice through the universe in x and y at some fixed z. We're going to imagine the Earth is later going to form, say here at the origin. And I picked 3 Fourier modes. This is what they look spatially. So this is larger and larger k, so smaller and smaller wavelengths. And each of these modes is going to, so this is the Fourier mode. So these won't move, but their amplitudes will change as I evolve those equations, right? And the rate of change will have to do with this wavelength. And so in this top panel, I've got the mode amplitude. And the x-axis is time. And so if I start these at the Big Bang at time equals 0 here, the left side, and I let them evolve for a while, this largest scale mode will evolve the slowest, this guy a little bit faster, this guy even faster. And this stops here. I've stopped it as at where the sound speed goes to 0. So one thing you might ask looking at this is, why have I put all of these to start at their maximum and at the same amplitude? And that's a good question. And I don't really have time to get into it in this talk, but that's basically the initial conditions predicted by inflation. Or put another way, this is why inflation was created, to solve why this appears to be the case. And what inflation gets us is that it says that the initial conditions of all these modes were at some amplitude parameterized by AS and some very, very small tilt. So in this cartoon version, I haven't actually put a tilt in. So these are all at exactly the same amplitude. In reality, the fact that NS is slightly different than 1 means that these smaller scale modes are going to be at a slightly different amplitude than these larger scale modes. But it's actually quite close to constant. So, okay, so let me now run this picture forward. And this is what happens, right? So this is how each of these different modes evolve. Basically, this one undergoes 1 fluctuation. This guy goes down, but then at the end ends up at 0. And then this one undergoes a full fluctuation, right? So I picked these modes specifically because this was the case, because basically this is the fundamental mode, and this is, in fact, it's in language of music, you could say this is a perfect fifth, and then this is the octave higher than that. And so this is what these modes look like now, frozen in at this point when the sound speed goes to 0. We don't actually get to see this, obviously. What we get to see, right, is just the little bit that's the last scattering surface that's going to scatter to us today. And we really see the co-addition of all these different modes on the last scattering surface. And so we get to see something like this. But what I hope this makes clear is that basically this largest scale mode here that underwent 1 fluctuation, that basically corresponds to the peak in the CMB power spectrum here. And this mode here that actually underwent 1.5 and so ends up 0, that's basically this minimum here. And so the series of harmonic modes gets represented in terms of the angular power spectrum today in this fashion. So looking at this even a bit closer, if you look at the length scale that's imprinted by the biggest, largest scale mode on this last scattering surface. So for example, it's the typical size, typical distance, angular distance between hot or cold spots. So here between two cold spots. If you look at this angle, so we can calculate that angle today, and it's basically this distance RS, which has to do with how long did that mode have, longest wavelength mode have to oscillate before the sound speed went to 0. And we see the angle, so there's a distance to last scattering dA. And you can calculate this. These are all distances, and basically they're related just to Hubble lengths, right? And so what's relevant here is the Hubble length at recombination when the universe was matter dominated. And so this is roughly going to vary like 1 over square root of the matter density. And the distance to recombination is what's relevant to is the Hubble length today. So that's roughly 1 over the energy density of dark energy, say. And so here's one way in which these parameters come in. And if we measure this angle, we get a handle on these two quantities. But now there's at least one thing that's about this cartoon kind of that I've given you that's not entirely accurate, you might notice, which is that if this is totally true, the CMB spectrum should just be these totally evenly oscillating modes, when in fact you've seen the CMB spectrum and it drastically drops for small scales, right? So why does it do that? So there's a number of reasons, one of which I can give you within the context of this example, and that is the following. So I don't know why 0.2 inches has appeared on my slide, but ignore that part. So this last scattering surface actually had some width, right? So not all the photons came from exactly on this sphere. Some just happened to scatter a little earlier, some a little bit later. So we actually see an integrated, we see a bit of a different, from each little slice. And for the very largest scale modes, that doesn't really matter because those modes just don't vary across this slice very much. But for the smaller scale modes, they actually do vary across this slice very much. So you add a bunch of these together, and let me exaggerate, make this an even smaller scale mode. You add a bunch of these together and they cancel, and it goes to 0, and you get damping. So this is one of a couple of effects that cause this, but it leads to the CMB spectrum looking like so, where this is in blue, so at small scales it really drops here. Now, fortunately, there's an equation from this paper that models the amount of damping that you get, and I can use that to just remove it from the spectrum. And when you do that, you get something that looks like this. So this now actually does indeed look a lot more like what you might think, just a bunch of constant oscillating modes. Although we're not quite there yet, because there's still some structure here. And to explain that, I have to go back to this equation, this harmonic oscillator equation, and now talk about this driving force term. And so you'll remember from a harmonic oscillator, when you drive it with a constant force, what happens is that you just get an offset, right? It just oscillates the same, but around a different 0 point. So that comes into explaining why these even and odd peaks appear to be the odd peaks appear to be lower than the even peaks. And that's coming from the fact that basically gravity is coming in as a driving force. It's shifting the 0 point of this oscillation, which then to look at the power spectrum, you square it. And so basically every other peak, the ones that were positive are going to be bigger, but then the ones that were negative squared will be smaller. And the amount by which that manifests itself has to do with the frequency of this oscillator. So a really slow oscillator has its 0 point much more offset by a constant force than a very fast oscillator. And the speed of this oscillator is controlled by the sound speed, which if you change the baryon density, you control how fast that sound speed goes to 0. So basically, as you dial the baryon density here, you're going to change the ratio of even to odd peaks due to this effect. Similarly, there's one other thing you see, which is even that, actually this first peak is definitely lower than that one and that one and that one. So there's still something left. And this turns out to be this matter envelope effect. And that has to do with the fact that if you drive an oscillator with something that's in phase with it, it's going to boost the oscillations. And that's exactly what's happening to these modes out here at smaller scales. Basically, these modes start oscillating and at the same time, the gravitational potentials that they're oscillating in decay, and they get an in-phase kick from this effect. And so these modes actually all get boosted. This happens because the universe is radiation dominated through most of when these guys are oscillating. But the universe turns out to be matter dominated right around when this guy is doing most of the oscillation. And in the matter dominated universe, you don't get this decay of modes, you don't get this in-phase kick, and this guy here doesn't get this enhancement. And so you see that basically they follow this envelope. And where exactly this envelope falls is controlled by this matter density parameter. All right, so hopefully that's given you a bit of an idea of how these different parameters affect the CMB spectrum. What we actually do to compute parameter constraints is that we calculate this model, and then we use Bayesian inference and run MCMC and get posterior constraints on all of these different parameters. And they look something like this. So this is actually showing you from two different subsets of the Planck data. There's Planck L less than 800. So this actually basically reproduces what you would have gotten if you had just done it with WMAP, because those are the large and intermediate scales where they're basically the same. And if you add in all of the Planck data, so the small scales that really Planck is unique in seeing, you get the orange lines. And so you see that basically parameters, constraints tighten up. There's some shifts. For example, to single out one that's definitely generated some interest. So previously, the best constraint on the Hubble constant from this, assuming lambda CDM, was something like this, 70 plus minus 1.2. So we've almost halved that error bar. But there's also a shift to a lower Hubble constant. And definitely this has attracted some attention. In fact, so one of the reasons is because there's other measurements of the Hubble constant, for example, right? There's measurements, for example, from Cepheids and supernovae. I believe you'll hear about this tomorrow morning in Rachel's talk. And in fact, these shifts from WMAP to Planck made it so that we're now in slightly more tension with these local measurements. And again, I'll remind you, anything about this lambda CDM model breaking is extremely exciting because it means new physics. And the question is this a hint of new physics? Or is it a hint of systematics in Planck or in one of these other probes? So this is an interesting question. This is not the only area where some of these shifts have caused tension. For example, there's some tension with galaxy weak lensing when you look at this omega matter and this sigma 8 parameter. Again, basically the point here is that this red contour from Planck is a bit outside of the others. So this is all interesting. And also within Planck, right, we saw there were some shifts between if you did just intermediate and small scales versus, just large and intermediate scales versus everything. And so one thing we wanted to do was verify that within the Planck data there weren't any internal inconsistencies, and basically that those shifts that you saw were okay within the Planck data. And so this was in this work, this Planck intermediate paper that you see here. And what we did was, we just wanted to answer the question, are those shifts okay? And the way that we did that was basically with a massive set of simulations. We simulated the Planck data, and we simulated analyzing it, and we did this thousands and thousands of times, and built up a distribution of what you might expect these shifts to be between these different L ranges, and compared it to what we actually saw. So that's what you're seeing. This is the shift between L less than 800 and L less than 2500 parameters in these parameters. The orange dot is the shift we actually saw. For example, here's H naught. So H naught, we saw a shift of about 3 kilometers per second per megaparsec. And the blue contours and cloud are the simulations. And so from this, we can get an idea of how unlikely is this shift. And from here, you see, okay, they lie along degeneracy directions. It looks, maybe so you want to quantify this more. So what you do is you pick a statistic, and then you compute it on the real data. You can compute it on each of these simulations and get a PTE. And so, for example, for this chi-square statistic, where we compare that point to the covariance of the blue points, we get a PTE of about 1.4 sigma. So this is really not that much at all, in fact. And this is even a bit smaller than other more rough versions of this calculation that had been done before. So in terms of Planck consistency, this was good to see. We can also look at, for example, a different statistic, the maximum outlier. Doing it with these simulations essentially takes into account the look elsewhere effect. And 1.7 sigma is the significance that we find. So again, really pretty okay. And we did this not just comparing this nested set, but also just low versus the small versus the large scales. and cutting at 1,000 instead of 800. And then we also did this also at like 20 other different cuts. And so we really explored this just extensively, basically finding that all of these significances are really not that large. So, as you might imagine, that was quite a lot of computing time to each of those required, simulating the entire Planck analysis and doing all of this for tens of thousands of simulations. And that leads me into the next part of the talk, which is this volunteer computing project that I run called Cosmology at Home. So this is a volunteer computer cluster, which means that basically anyone can join. You all could log in right now. In fact, I invite you to visit our website and check out our interface, which is state-of-the-art in 1997. And basically, while you're not using your computer, after you install our program, we can use it. And we can run, and at the moment, it's running Planck-type analyses. And this is really cool. People can go on and they can make profiles. I just picked a couple to show you kind of who these people are that actually do this. This guy, I guess, gets the honor of going first because he lives in Paris like I do. There's people all over the world. He's in Brazil. There's mothers. There is not just the administrator, me of Cosmology at Home have great mustaches. Our members do too. People write really pretty, really well written, things about the universe that they know that they're interested in, which is pretty cool. Some people are pretty weird. There's a lot of weird profiles on here. This being the internet, some of these volunteers are in fact cats. And so anyway, we have across the whole globe, so I did this in 2015 by IP addresses. These were the computers that had computed a result for us in that month. And so it's about 10,000 active computers per month, sort of all over the world. And one thing, it may shock you to believe, but people really care about fake internet points. And we are no exception. And so people get credits for doing these computations, and they compete with each other. And so there's rankings. So when we did this Planck analysis, we actually had a contest, and we gave the top 3 people, we thanked them in the acknowledgments. You can go look in that Planck LI paper there. These 3 names are in the acknowledgments. This really got people excited. And people also compete in teams as well, so it's pretty cool. So to give you a sense of how useful this actually is, or how much computing power there is in this, so this is a cluster at my institute that is shared by like 10 people. It's about 100 nodes, and Cosmology at Home is about 3 times more computing power than that. It's not the same kind of computing power as your traditional MPI cluster, so that's for sure. It's quite useful still, but in terms of raw, say, floating point operations, it's about 3 times more. But we're not the only project. In fact, there's basically hundreds. We are maybe top 10, top 20. And if I look at the biggest one, SETI at Home, this is Search for Extraterrestrial Intelligence. I think this is the original, in fact. Those 2 bars that you see there now are these little slivers. And this is how much computing power just one of these top projects can have. So this is really cool. This is a really significant amount of computing resources. It's something I'm interested in. I tell this whenever I give talks, but basically, even for us now, there's times where we have more computing power than we know what to do with. So if anyone has interesting ideas of what they want to do, come talk to me, because I think that would be cool. So yeah, and this really helped us compute those simulations that we needed for the Planck results. So in the final part of my talk, let me just turn to the following. What's to come from the CMB? So in this talk, I focused really mainly on this temperature anisotropy spectrum. I mean, really exclusively on this temperature anisotropy spectrum. Those photons that we get, we don't measure just their temperature, we also get their polarization. And so you can make polarization power spectra, and there's polarization now, so there's 2 degrees of freedom, and so you can do something that are called E modes and B modes, kind of an analog to electromagnetism. And this is the E-mode power spectrum. It looks like this. You can see it's smaller than the temperature power spectrum by several orders of magnitude, so it's harder to measure. But it's been measured, and measurements are very much ongoing. And then, more interestingly perhaps, though, there's the B-mode power spectrum. And the B-mode power spectrum is more interesting because basically we think it should be 0, except if inflation, or if something in the early universe generated a background spectrum of gravitational waves. And if it did, then those gravitational waves interacting with the baryon plasma at last scattering create B-modes. And depending on the amplitude of gravitational waves, which is this new parameter now called R usually, you can have some B-modes. And if you detect this, this is extraordinarily interesting because it tells you about inflation, it tells you about the energy scale of inflation. Some people would tell you that it confirms inflation happened. And so this is really possibly one of the most fundamentally important things that could be discovered with a CMB. And in fact, this is actively this is really actively driving the CMB community right now. There's a wealth of experiments that I'll just show pictures here without naming names, but there's really a wealth of experiments going after this signal, and other interesting physics that you can do with this polarization. One difficulty for the polarization measurement, for this B-mode measurement, is that there's actually another thing that creates these B-modes, which is gravitational lensing, that just distorts the CMB, and it turns out to turn E-modes into B-modes. And as you can see here, this is the predicted level of this contamination, these lensing B-modes. And for this particular value of R, this really is a big contamination on top of this signal that you're trying to measure. And a really active area of research right now is trying to figure out how to best get rid of this contamination and do delensing. And this is one thing very recently I've been really interested in working on, and we quite recently published this paper on this method, which I don't have time at all to really get into, but just to give you kind of a couple of pretty pictures. But the idea is that we're given noisy data, we're trying to reconstruct what these so-called delensed B-modes, so the B-modes after you've removed the lensing, look like. And for some particular simulated patch of the sky, about 100 square degrees that we did here, our reconstruction looks like this. And what's cool about our method is that it's based on Bayesian inference, and so you get not just the best fit, but you get samples from the Bayesian posterior of this delensed B. And so, for example, flipping through some of these samples, it looks something like this. And so this is not just a pretty movie, it is actually mathematically draws from the posterior, so they tell you about basically the exact posterior knowledge of the delensed field in these different points, and is useful in a number of different ways. And it's also totally optimal, and along with these different samples of B come a sample of R, this amplitude that we're trying to measure. And if you make histograms of these, just like you do with normal MCMC chains, you get constraints on R, for this particular simulated data that we did here. And what's really crucial about this is that this is actually statistically optimal. And this is one of the things that's difficult for a lot of, one of the reasons this is difficult, which is a lot of the estimators that currently exist for computing these estimates of R are statistically suboptimal. And doing the optimal calculation is much more difficult, but actually can improve constraints. And here, at least in the simulated case, we've shown that we can do it. So, to conclude, I talked a bunch about the Planck mission, and I talked about how that the simple 6-parameter model agrees with lambda CDM. Hopefully the explanations of the physics behind it were useful. I showed you this exercise with simulations where we determined that the Planck data appears internally consistent. A lot of that was based on this cosmology at home thing, so please feel free to talk to me about that. And yeah, so there's lots of interesting CMB work looking forward in the polarization and with all of those experiments that you saw. So thank you.
Thank you so much for your talk. Are there any questions? All right. was interested in the tau yes constraint. And there's, a year ago, there was a few papers by Wayne Hu and Aranda and Morgenstern.
Mm-hmm.
And the point they were making was based upon the publicly available LFI data, that if you use the too symmetrical or simplified a model of the redshift dependence of the ionized fraction during reionization, and then did your fitting procedure, and you got a small tau yes, smaller than had been in the previous generation of WMAP, let's say. And they showed that if instead you took a more physically realistic or complicated history, including an earlier reionization in a non-symmetric way, you push tau yes to a higher value. And so I'm sort of I was anxiously waiting to hear what HFI data,
yes,
when addressing the same issue. And as of late spring, Planck colleagues I was running into the meetings still haven't anything to say about that. So
that's right. Well, what I can say for sure is that, so on the one hand, I'm limited by what I can say by being in Planck and this data not being totally public, but what I can definitely say is we are for sure looking into that model dependence of the tau constraint, depending on the model of reionization that you picked, motivated by these papers that you mentioned.
All right, then we had a question in the back.
Hey, wonderful talk. Is this on?
No.
I'm great. Hello?
It's better.
Hey, great talk, thanks. I have a question. Would you talk a little bit more about the station-out discrepancy, if you can?
Sure.
There's a paper by Spergel that claimed that maybe using different data sets, maybe the shift corrects itself a little bit, and then Check That Inst group also put out a paper that talked about the discrepancy with the SPT high multiple data and possible systematics there. Or is there new physics you want to tell us about?
Let's see. So there's a lot there to answer, but let me try. Okay, so let me address the one of the things that you mentioned about different data sets. So the one thing that's often brought up, it's not on this plot, but the H0 constraint from Planck and the H0 constraint from the South Pole Telescope, which is essentially the next tightest constraint on H0 besides Planck and WMAP. The South Pole Telescope one tends to favor values that are closer to the WMAP central value, but the error bars are big. But there's been a similar question raised about whether, okay, are Planck and SPT in agreement? And whereas here, you know, what you can say is that, well, the reason this shifts from here to here is because of those small scale modes that WMAP just couldn't see. And so this is fine that it shifted. You don't really have that with Planck and SPT because those both measure the small scale modes well. I mean, there's still some level of expected shifts, but you know, they're measuring the same modes. And so in the last 6 months or so, though, actually the SPT collaboration has put out a really nice paper that very carefully compares Planck and SPT map, both at the map level, and then computes parameters, computes H0, does some similar type exercises to the ones we did in Planck with computing. And they find things are consistent at about the 2 points a bit sigma. So that's the level that it's at. And that could be interpreted in however you want. Yeah. Let's see. Maybe I could take another question and then answer the remaining. Yeah.
My question addresses the same topic. Does your output value of H0 change very much if you change your priors? And have you allowed your priors to change with time as more information external to Planck has been produced?
Right. So So I think there's and maybe this is what you mean, but I think there's two ways in which priors come in here. So one, there's assuming the lambda CDM model itself. That's certainly a prior, and that's a very, very strong prior, in fact. And without that, the Planck constraints on H naught are much, much wider. In fact, it's probably balloons by a factor of 3 or 4. And so because of that, you might be tempted to explain this discrepancy with just saying, oh, okay, so let me open up the, not assume lambda CDM and then find the model extension that makes it so Planck H naught goes back here. And I think if there had been like if it had been really simple, if it had been, oh, there's 4 neutrinos and H naught is 7, in that case, for example, H naught from Planck jumps up to 72 or 1 or something. And if everything else fell beautifully into place, I think that would have been super compelling. But there's basically no model where that works so simply. So that's been part of the reason. That's not been, we've stuck with this lambda CDM model, with such a strong prior per se. But then there's a second thing, which is just within lambda CDM, you could take a flat prior on AS, or you could take a flat prior on AS e to the minus 2 tau, and those are different things. And I don't know which one is more reasonable, to be honest. And that definitely has been checked, that we're not sensitive to stuff at that level.
All right, so I think we're running out of time. So let's go ahead and thank Marius again.